The discoveries of the James Webb Telescope have sabotaged the case for the Big Bang. The James Webb Space Telescope has just conveyed an outright exhilarating disclosure, truly sending shockwaves through the worldwide universe of material science. Through a single amazing photograph, it has obliterated long-standing discussions, leaving researchers significantly astonished. The age of hypothesis is over, as Webb's most recent capture is both visually beguiling and a game-changer that contributes to form our convictions, impacting discussions among researchers. This photo has unequivocally prompted new strategies. The exquisite picture captured by the James Webb Space Telescope is rethinking how we might interpret the universe. Join us as we explore why it is getting attention and how James Webb's findings are closing discussions in material science with a groundbreaking image. The fundamental difficulty with astronomy is that researchers cannot agree on how old the universe is or how quickly it is growing. This unanswered phenomenon has perplexed scientists across generations, prompting various examinations to find answers. Cosmology, the field of exploration focusing on understanding how the universe was made, how it is assembled, and how it has changed over time, has seen significant improvement over the past 100 years. The current broad cosmology model, the theory of the Big Bang, proposes that the universe has been expanding from a hot and dense state for around 13.8 billion years. This expansion is measured through the Hubble constant, which indicates the speed at which the universe is expanding. However, measurements of the Hubble constant are not unanimous. Estimating the Hubble constant can be broadly categorized into two groups: nearby measurements and early universe measurements. Nearby measurements involve the study of galactic collections of the universe. For instance, Psi variable stars and type Ia supernovae act as standard candles to gauge the Hubble constant. Because of their brilliance, astronomers can measure how the universe's expansion affects the velocities of these objects to determine their distances, and thus calculate the Hubble constant. The second group involves the estimation of the early universe. Researchers use observations of the cosmic microwave background, CMB, radiation, the luminosity of the Big Bang discovered in the 1960s. The CMB reflects the microwave radiation of the early universe when it was only 380,000 years old. By measuring the small temperature and polarization fluctuations emitted by the CMB, space experts can determine the age of the universe and its rate of development. Yet here lies the issue. The results of these two methods do not match. The outcome found through nearby measurements confirms that the universe is expanding faster than what we gauge based on CMB data. Due to these differences, researchers have been striving to find the reason behind the conflicting results. Further research is being conducted to learn more about the universe's secrets. As things stand, the discrepancy in measurement suggests that there is either new science we have little insight into or errors in one or both methods. Thanks to the James Webb Space Telescope, we can see into the dark universe more clearly than ever before. The telescope can reveal the faintest and most distant elements, planets, and galaxies we would not have thought possible to see. Researchers naturally expected that data from the JWST would help us in precisely computing the Hubble constant. However, the initial flood of data has surprisingly made matters more complex. It has provided new insights that are not consistent with what we thought we knew. Might this data lead to a new hypothesis and upset our understanding of space? If so, we would need to review our understanding of how the universe works. For instance, we might discover particles and forces that have never been observed, or might need to reconsider dark energy, an unexplored element responsible for the accelerating expansion of our universe. To date, the ways we think about space have evolved as we continue to discover new things. For instance, in 1965, when researchers discovered the cosmic microwave background radiation, it strongly supported the theory of the Big Bang. Previously, researchers believed that the universe was eternal, consistently expanding at a uniform rate. However, new evidence proved that was not true. Furthermore, when we found out towards the end of the 1990s that the universe was continuously growing, we discovered dark energy and its impact on the universe's development. Hence, like clockwork, when we research something new, we question whether it fits into our existing framework. If not, we develop new ways to understand the universe better. Thus, the issue we face in cosmology today could lead to the discovery of significant answers about the universe. While the issue is challenging, it is also exciting as it propels us to develop more advanced tools to explore space. This cosmological quandary also unites researchers from various nations, each eager to learn more about the universe. Above all, it shows that science is continually changing and evolving as we learn more about space. Alongside the Hubble tension, there is also a challenge called the SA strain, which pertains to the spatial distribution of matter in the universe. This can be used to create a principal image of the universe and understand how it has evolved. Astronomers refer to this phenomenon as unevenness because there are areas of space with tightly grouped galaxies, while other areas are sparse. Researchers will use various methods to measure this unevenness. One way is to study how light from distant galaxies is twisted by the intense gravity of large objects, such as galaxy clusters. This twist, called gravitational lensing, provides a way to examine where matter is faint because it does not emit light. Analysts also use the cosmic microwave background, CMB, a glow from the beginning of the Big Bang. This light has been traveling for around 13.8 billion years, carrying information from the early universe. Through CMB analysis, physicists can understand how the universe became clumpy at its birth, which should match the observational unevenness of the universe on a large scale. However, these results do not align. The CMB's clumpiness, given by the non-round gravity distribution model, suggests that the matter distribution in the early universe was more homogeneous compared to what is found using gravitational lensing. This suggests that there may be something we are not considering in our explanation. This brings us back to the idea of dark matter. What exactly is dark matter, and how does it function? The truth is, the issue remains unanswered. However, all hope is not lost as the James Webb Space Telescope, JWST, is set to redefine the field of space science. With its high resolution and camera sensitivity, the telescope will examine early periods of the universe and explore the first galaxies and stars formed, making it possible to improve measurements of cosmic expansion and matter distribution. These fundamental questions will require specific observations and possibly new methods from a theoretical standpoint to solve. Whether the findings mean greater significance for dark energy, discovering entirely new physics, or gaining a better understanding of dark matter behavior, the results will be far-reaching. Solving the universe's mysteries is like working out a puzzle with countless pieces while blindfolded. Researchers are like thorough investigators focused on and passionate about solving these mysteries. The latest undertaking, called Project Flamingo, is evidence of NASA's increasing enthusiasm for scientific investigation. Using one of the world's most acclaimed supercomputers located at Durham College in England, Project Flamingo is a remarkable achievement in computational development. It required more than 50 million hours of computer time and features 35 processors. The operation highlights the scientific community's determination to explore the universe thoroughly, focusing significantly on dark matter, the mysterious substance that neither emits, absorbs, nor reflects light, but is inferred to exist due to its gravitational impact on visible matter. The approach of Project Flamingo is different from past simulations, involving all potential forms of cosmic elements, from galaxies with extraordinary gas content to stars and black holes at the universe's center. Through this systematic approach, the gradual change in the universe's portrayal was generated from a fundamental sketch. The motivation behind ambitious projects like Project Flamingo is clear: to explain cosmic structure where measurements seem flawed and do not fit into the universe's design. This difference in measurements shows a significant gap in our current understanding of the universe's functions. If these measurements were comparable to musical genres, they would be like jazz and classical music, each having its approach while still related. Flamingo endeavors to combine these different perspectives and sharpen our individual perception of the universe. However, despite its refinement, cosmic tension persists. This tension continues as humbling evidence that we have yet to resolve a significant part of the mystery surrounding us. The universe appears reluctant to share its secrets with us easily. Each new data point and simulation model added to our toolkit, like Flamingo, opens up an increasingly large new universe with new challenges to address. It is a continuous journey where each answer leads to more questions, opening up a whole new layer of inquiry. This shows us that the nature of our quest to solve the universe's secrets is complex and ever-changing. Since Edwin Hubble made his notable discovery of the expanding universe in the early 20th century, the pace of our understanding has been astoundingly fast. Scientists are continually making specific discoveries about the universe's size, including the Big Bang theory, dark matter, and dark energy. They have studied the cosmic microwave background, CMB, and meticulously recorded the positions and velocities of galaxies with increasing precision. Each of these achievements is like obtaining a new critical piece of the cosmic puzzle. This has driven us to strive for a deeper understanding of the universe. Indeed, the universe is shrouded in mystery, and it might be dangerous to uncover its realities too soon. At each investigative step, researchers added refined theories, altered models, and carefully characterized inquiries. The theory of the Big Bang was once very controversial, but is now considered a critical piece of scientific knowledge. Similarly, dark matter is no longer a speculative idea, but an undeniable key element of a vast riddle. The discovery of dark energy, an unknown force pushing the universe's expansion, was made in the late 20th century, and is now one of the essential pieces of understanding the universe. Let us also consider technological advancements such as the Hubble Space Telescope, LIGO, and the James Webb Space Telescope. Each has opened new perspectives, permitting us to observe gravitational waves, distant stars, and the earliest phases of the universe. Each innovative stride takes us closer to understanding the mysteries of the cosmos. As we stand on the brink of new revelations, perhaps we are uncovering answers and engaging in a more comprehensive and nuanced comprehension of the universe's operations. It is an exhilarating and continuously progressing journey filled with marvel and discovery. Sure, let's delve deeper into each aspect of the discoveries made by the James Webb Space Telescope, JWST, and how they challenge our current understanding of the universe, particularly the Big Bang Theory. The Big Bang Theory and Hubble constant, local versus early universe measurements. There are two primary methods to measure the Hubble constant. 1. Local measurements. Psi-8 variable stars and type Ia supernovae act as standard candles to measure distances within our galaxy and nearby galaxies. Tension in local measurements. Local measurements using these methods suggest a faster expansion rate than the measurements obtained from the early universe. 2. Early universe measurements. Cosmic microwave background, CMB, is the afterglow of the Big Bang. Measurements of the CMB, such as those from the Planck satellite, offer a different value for the Hubble constant, generally indicating a slower expansion rate. The discrepancy between these two sets of measurements is known as the Hubble tension. The role of the James Webb Space Telescope, JWST was designed to explore the universe in unprecedented detail, offering insights into the early universe, galaxy formation, and more. His findings have raised new questions and provided data that sometimes conflicts with our current models. Key discoveries and their implications. 1. Early galaxies.